Okay, let's kick off, shall we? I think that's probably enough time. Hello and welcome to today's webinar from GeoSpock on benchmarking the mobility data challenges of the future. Just before we begin, a couple of practicalities. We will be recording this webinar, so no need to do that yourselves. We will share the link with you when it's ready, probably early next week sometime, so you can then distribute that accordingly as well. Feel free to share onwards. And if you have any questions as we go along, hopefully you can all are familiar with the Zoom setup. But if not, in your bottom panel, I think there should be a Q&A button. If you click that, you can put a question in there, and when we get to the end, we should have a time to go through a few of those as well. So hopefully that's all clear, and hopefully everyone can see my screen and hear me talking. So thank you very much for coming. And with that, we can get cracking. So benchmarking the mobility data challenges of the future. I'm Mark Porter. I will kick us off today and then bookend us again at the end with a bit of context around what we're talking about here in the mobility sector, what we mean by those data challenges. And I'm joined today by George Phillips, one of our data scientists here at GeoSpock, who's really going to talk you through the interesting meat of the presentation around how we built a giant synthetic data set to emulate those challenges and how it informs our product development process here at GeoSpock. So say hi, George.
Yeah, morning everyone. I hope you're having a nice day.
Great, thanks. And then for those of you who are maybe a little bit less familiar with GeoSpock, we are a Cambridge, UK-based technology company, and we're focused on building a database that is optimized for what we call connected device data. Mobility is at the heart of that type of data. It is effectively devices like your mobile phone, like cars, that are out in the physical environment, moving around, gathering data automatically or possibly by human-generated means. This data is really rich in insight potential, but it's really complicated, complex, and often it's very large as well in scope as it accumulates. And our database technology is really designed to optimize the accessibility of that data, make it as cheap and make it as affordable and make it as rapid to get analytics and get insights out of it as possible. So that's us in a nutshell. And mobility is obviously really close to our hearts because it kind of forms the core of that connected device data. So just to set the scene a little bit, mobility maybe as a term is a relatively new one. I think probably most of the people on this call are probably fairly familiar with it. And what we mean by a GeoSpock really is any data that is collected or applicable to the movement of people from A to B. So obviously the connected car, which is maybe going to be the focus of this conversation, is a core piece of that, but connected public transport, connected buses, connected trains, even connected maritime can also be kind of considered mobility devices and mobility generating industries. But also ancillary devices, your mobile phone, maybe even your wearable watch, is generating data which acts in a very similar way and has very similar characteristics to that mobility data and can be used in many cases for the same types of applications. So although it's a relatively new sector, it's a very data-driven, data-heavy sector. And that's really where we see some of the challenge and opportunity lying at GeoSpock. And just to give you a sort of outline and an overview of the scale of that issue or that challenge, I've got a few kind of quotes for you just to set the scene. So Wajo, a company who are primarily involved in the kind of collection of connected car data and providing that onwards as well as sort of insights, they reckon that connected cars generated estimated 95 petabytes of data in 2019. So this is 2 years ago. Connected cars were already generating an absolutely gigantic amount of data collectively. So this is just, the inbuilt sat nav, the inbuilt telematics black box, the SIM cards that are now put into modern vehicles that enables them to transmit data back to hubs and back to service providers. So it's an absolutely gigantic amount of data, way bigger than what most organizations treat as constitute big data as today. So this is a massive step up again from that. Of course, when we talk about connected cars, we have to have one eye on the future. And of course, the autonomous vehicle is probably where the ultimate connected vehicle lies. Intel have produced a graphic recently that reckons that each connected car could produce 4 terabytes of data every day. So this is an absolute, if we think Wajo's predictions are large now, this is an absolute tsunami of data that is yet to come in the near future from the autonomous vehicle sector. And this has obviously led to a lot of excitement in industry and a lot of recognition of the value potential that's tapped up in that data. So much so that an executive at Deutsche Telco recently said that vehicle data is more profitable than the car itself. And I don't know about you, but when I think about my car and how important it is to my life and how important it is for me for being able to move around in the world and how much value I place on that ability, to say that the data that's being generated by that car is more valuable than it is a really astounding statement. And so, you know, whether you believe these facts and figures down to the T or not, what you can see is that there is a huge amount of data that's already being produced. It's only going to get bigger and it's only going to accumulate more rapidly in the future. And there is a huge amount of value locked up in that data. And I'm going to take you back to a quote that I'm sure you've heard many, many, many times before, which is, or the old adage that, you know, data is only valuable if you can get decisions out of it and make decisions from it. And we at GeoSpock believe that, you know, that's not just a data collection challenge. You know, we're already collecting huge amounts of mobility data here. It's also an infrastructure challenge. How do we make that data that we are collecting at such pace accessible, such as actually possible to thread the needle through the haystack and make decisions based on it in an affordable and cost-effective and rapid manner? And we believe fundamentally that that is a digital infrastructure challenge. And we believe that new digital infrastructure is going to be needed to solve that challenge. And that's really our core focus as a company, building that database technology to be that new digital infrastructure. And I have some evidence here to show why it's such a challenge and why the existing kind of technologies and digital infrastructures of the day are already creaking at the seams. So this is just quickly a third-party benchmarking exercise that was conducted last year. So the data sets are 8 billion rows up to 80 billion rows, so increasing orders of magnitude of data size, running the same query, which was a spatial query, so a query that's very common in kind of mobility and analytics, looking at kind of where type questions of a data set. And we ran this, this was run, sorry, by a third party on a major cloud analytics database on those varying scales. And you can see, looking at this, that analytics is costly and it's time consuming on these data sets, right? It took over a day and cost over $100 to run it on just 8 billion rows. It took nearly pretty much a week's worth of time to run it at 40 billion rows and cost, you know, $600 plus. And it didn't even work at 80 billion. And just to contextualize those figures, 80 billion obviously sounds like a huge amount of data. But in the world of connected vehicles, where maybe the sampling interval of the vehicle is 1 second on GPS traces, and you've obviously got thousands of vehicles potentially coming in, sending in data. These numbers will quickly become hundreds of billions, if not trillions of rows, as we're going to see shortly. So really, you know, the digital infrastructure of today is already struggling with data sets that are an order of magnitude smaller than are going to be produced and are being produced by the mobility sector today. And so at GeoSpock, you know, our technology is designed to try and help make those numbers, that 1 day, that $125, that 5 days, that $600, as small as possible. And you know, our results so far are pretty impressive. You know, orders of magnitude faster, orders of magnitude cheaper for the same queries at the same scale. And of course, we work at the largest scale, which is also nice as well. This is really great. But we want to keep building, we want to keep developing our product further. And to do that, we need data sets of the right scale to be able to stress test our system, stress test that new technology and stress test that infrastructure. And we want to do that on mobility data, which is at scale, right? So we want those 100 billion rows, 100 trillion row data sets, so we can do that stress testing. So when we've done this benchmarking, that was great. And we then cast our eyes out, where can we find these data sets that are big enough to be able to do stress testing properly on? And ideally, we scoured the public domain, because ideally we would use public data for this. Public data is affordable. It's also transparent and cost effective and shareable, makes results replicable much more easily. So the kind of gold standard for testing is to use a public data set. And I'm sure that many of you in the mobility space, working in the mobility space, may well be aware of the New York City taxi data set. So this is kind of maybe the benchmark gold standard of mobility big data that's available in the public domain. And it's a data set of trips of New York City taxis over a time period. 1.1 billion trips is encapsulated in the data. So it sounds a lot, and it's a reasonably large data set. It's 306 gigabytes in size. But let's think back again. A couple of slides ago, I said that, you know, connected vehicles are producing 95 petabytes of data. So actually, the New York City taxi data set is a millionth the size of the data that's being generated across the mobility sector. So is it really a large enough data set to enable stress testing of digital infrastructure? If we were talking about physical infrastructure and I was building you a bridge and I told you I'd test that bridge with a load a millionth the size that it needed to be able to carry on a day-to-day basis, you'd probably tell me that you had some concerns. And yet that's the case that we are in today in our digital infrastructure. The data sets that we're using to do those tests are simply not big enough to be able to accurately extrapolate out to the future where we're going to have these massive, massive extreme data environments. So is it big enough to stress test? Probably not. It's a great resource for learning, but for stress testing, probably not big enough. And so we scoured the internet, and if afterwards anyone does have any suggestions for large public data sets, please do get in touch, because we scoured the internet and we scoured our kind of knowledge circles, and we couldn't find one. And so I'm going to pass over to George, because in the end, what we decided to do is make our own, and George is going to tell that story now. So over to you, George.
Yep, thank you very much. So once again, I want to say good morning to everyone. Hope you're having a nice day. And yeah, we're really excited to show you what we're working on today. So first, I'll talk to you about what we've built today. So just to set the scene, what we've based it around is the ERP system in Singapore. Now, in Singapore, they have a system called ERP, which is their electronic road pricing system. On the left, we can see there's a picture of the gantries they have throughout the city, and this is what they look like. They use it for a various number of use cases, things like distance-based congestion charges, monitoring of traffic, instance responses, that sort of thing. But they want to update their infrastructure. They want to look into doing a bit more 21st century. They do this through intra-car sensors. And basically, we've created a data set synthetically which can emulate this. So we want to show you an example of that. As you can see here, this is a subset of the data set and it's working. We took this from an SQL sample of latitude and longitude, and it shows it shows an emulation of what you'd achieve. We have different types of vehicles in the simulation working as they would in normal trajectories, going to where they will. And basically, this is done at scale. It's done at massive scale, and we created this through Uber's autonomous vehicle simulation system. We built upon that. So let me give you some background information about the data set. So we wanted to base it off of some statistics that represent the real world as they do in Singapore. So we built upon 8 million vehicles, because that's roughly the amount they have upon building it. And we chose to do about 4 million journeys every day for a year. So as you can imagine, that's quite a lot of journeys. And then when we create this, we chose different fields to look at. So we have the standard ones, like your when the sensor readings occur, where they are, some information about the vehicle, and also we just to add some extra detail, some the type of vehicle. So if it's a car, if it's a private hire, taxi, that sort of thing. And as you can see in the picture in the bottom right, we really do try and encapsulate real trips that are taken. And the amazing thing about all of this is it adds up to a massive data size when you compare to any other public one that we can find currently. So the size of our data set is actually 1.3 trillion rows, or 108 terabytes, which really is incredible when you think about it. So when I want to talk about this real life distribution, on the next slide, what you can see is there's a picture of all of these different starting points. This is where real journeys have started and then they go across. As you can see, there's clumps of data points in the outside and also the bottom of Singapore, showing the residential commercial areas. Because in real life, this is where people go. And when we take this data, we can then create realistic trips within the synthetic data. And in that way, we can tell, when we test, we get sort of realistic results. So some more information about dataset is in terms of the vehicle distribution, we also wanted to copy what they do in Singapore. So they have a majority of cars and high goods vehicles, as you can imagine, traveling from the port or up and away. And we also have some other notes that we created about dataset, things like the days that are similar. We didn't add any traffic congestion. And also, if a vehicle ends at one point at the end of the day, it may start at a different point. And there's a reason for this. When we created dataset, we wanted to get a good balance between the realism of the distributions, which is what matters, and also the speed at which we compute it at. Because if we try to do it as a very realistic simulation, the problem is it takes a much longer time and it's much heavier to compute. So the cost is also vastly increased. So these are things that we try to balance out so that when we do some testing on this data set, the results aren't going to be as accurate as you do in a real world situation, but the process of getting the results will be as accurate as we can possibly get. Now I'm going to talk to you about how we built the data set. And really, it's done in some pretty simple steps that we iterate over for every day that we have. So what we do for each day is we take our seed trips. We managed to collaborate with Singapore and managed to get some trips showing where places have started and ended. We generate some vehicles based on this distribution that we talked about before, 8 million vehicles, which add about 300 megabytes of data, which includes all of the vehicle registration numbers and the types of vehicles they are. Now, where it's interesting really is the second two parts. The first part is we generate some templates. So for each trip that's created, we have to basically route how those trips happen. So as you can imagine with Google Maps, they have a routing engine. We have our own routing engine we use and created to allow us to get these trajectories. And then what we do is we assign vehicles to take these trips throughout the day, which allows us to create the absolutely astronomical size of 108 terabytes of data, which, yeah, it's pretty incredible. It's 4 million trips a day, and these trips are chosen at random. So that way, when we pick them at random, it also chooses the more common trips more likely, so you get a reasonable distribution there as well. One of the things you might be thinking about is, so in terms of times, how does that work? We looked at the traffic in research on the Manhattan Bridge. We wanted to see how that worked. And when you include the inbound and outbound traffic, you can see it forms this sort of double peaked distribution, whereas a peak at rush hour times, roughly 9 a.m. and 5 p.m. So this is the sort of distribution we replicated with data. We want to make sure that most trips happen where they're supposed to happen. You're not going to have most of the trips in the morning at 2 a.m. because, again, when we grab the data and the way that we search it, we want to make sure that it reflects what happens in the real world. I want to come back to the picture that I showed you before of the I don't know what you call it, the different highways, I suppose. You can see here that the main ones are busy because of the fact that when we choose them randomly, you're more likely to get them to go down the normal routes that normal people take, which is done on purpose. You can see as well by the brown trajectory at the bottom, it's also a little bit wavy. You're probably thinking, well, why is that? That's a bit unusual. And the answer is, we're trying to replicate the technology that happens in real life. So we added some GPS noise there by, I think it's a few meters or so that when cars are traveling around, it's likely that through triangulation, it'll get a rough idea of where you are, but not exactly. So we wanted to make sure there's a little bit of noise so that when we look up data in the database, it'll emulate what you'll find in the real world. So we have about one sample or one sensor sample for every second, for every vehicle, every trip, every day. And that's what adds up to this massive amount of 1.3 trillion rows. I'll talk to you a bit now about how we actually created the system. So using the 4 steps iteratively at the start, we turn that into a Scala program. Scala is one of the best programming languages for parallel computation. And then what we did, we sent this to a Amazon EMR cluster, which allows us to basically give it to the driver, and the driver can basically take individual trips or lists of trips, spread them across different working machines and say, right, we want you to generate data on this day for this time. This is important because it allows us to compute them in parallel, which speeds up massively. We actually did this using 200 machines, and each machine had about, I want to say, 17 gigabytes of RAM. So you can imagine the scale of what was required to get this done. It was pretty intensive. And then once we got all the data, we put it into Amazon S3, a standard data bucket used in industry. And then from there, we can ingest it into our system. And then you're probably thinking, well, when it's in our system, what do we use it for? One of the greatest assets for us is benchmarking. We use benchmarking in various different ways. So we use it in different ways. So in the first one is we want to analyze when we do updates in configurations, or we want to look at different updates that we do on our release roadmap. We want to say, have things improved? And hopefully the answer is going to be yes. And we can check this by checking between them with this data set. We get a various number of queries, which I can show you as well. So in each individual benchmark, there'll be a general set of queries. And then we can see as well as so a number of things. One, we can see what's improved, and we can kind of tell the world that we're good at this sort of thing. But also there's very specific use cases that we see that we're really good at. We can say, okay, because we're so good at this, we can then target those sort of industries with marketing. And this really allows us to help expand. And one of the final actually is one of the important ones as well is discovering any unknown issues. So as a part of the quality testing, we do our benchmarking with this synthetic data set, and then we can say, if there's anything that we find unusual, we can then feed back to engineering, they can check and then make sure that the customers get the great experience they need. So as an example of some of the queries that we run, we have various types here in simplified form. So I guess, let's see. Yeah, there we go. So we have 4 different simplified cases here. So temporal, if you look at data over time, you want to see for a certain day, how has the traffic been, that sort of thing. If you're looking at a very specific area, like a bounding box, say there's an accident, you want to look at a very specific point and say how things have been affected. You can use aggregations. So this is looking at either a count of all the data, or you can average by hour, and we can create some analysis from that. And you can combine all of these as well to get use case testing, which Mark will talk about later, some of the use cases that we can actually use this powerful data set for. So when we run all of our different breadth of tests that we've created here at GeoSpock, it goes through our system, and then out at the end comes something called a recording log, which is done through PrestoDB. Now, what you can see on your screen is a list of properties and then the values that each of those have, and I'm going to break that down for you one by one first of all. So firstly, we have some information that's just general regarding the deployment. So our database, what type of machines is it running, how many machines, that sort of thing. So it's good to know when we compare the results. The second area is basically the real meat of what we want. So it tells us metrics out of the outcome of the query, things such as time taken. For example, you can see here, this one's taken roughly 60 seconds, how much data is read. But also with this, we can create our own metrics. So given that we know the cost of the machines and we know that the metrics here, we can kind of calculate the cost of queries, which is really useful for optimizing how things work. So if you look on the third part, you can see that this is specializing on the actual queries themselves. So you can see that here it's a query of about a 10-minute gap on the synthetic data set, and some meta information such as what benchmark was it ran from. That way, when we compare, we can say, take the same query from both of them, has it improved? And the last bit is just some meta information talking about PrestoDB, which is the overall system here, which creates the logs. But not only do we do testing on individual queries, we also do some testing on platforms that are commonly used. So for example, we look at Tableau. We want to make sure that when we do querying, because it runs through these sort of systems, that it creates a smooth user experience for everyone. So Tableau is one example, but there's many others out there, such as like Power BI, these sort of tools. We want to make sure that when we integrate with them and we run these queries, that when you're using them, that you get the sort of results that you're expecting. And the great part of the system is, and having this data set in particular, is we can use it over and over in terms of like continuous integration, really. We can say for every patch, for every configuration we want to test, we have this great realistic data set. We can kind of say, right, what can we improve on? And we can actually use this to affect our roadmap and well, make things better for not only ourselves, but for you as the people looking at the data set. I'll pass over to Mark now, because he's going to talk to you about some of those use cases that can be used with this data set.
Thanks, George. I think that's a really good insight into, the balance that we've struck between realism and making an accurate data set as accurate as possible, and practicality in running and generating such a large data set. And, just to reiterate, because we are effectively, using it for benchmarking our database, to an extent, things like congestion, obviously really important in the real world and really important in the end use case, but for benchmarking and for performance issues, we removed those so that they could we could generate the data set in a cost-effective manner, effectively. And so, I think when working with large data, everyone is always used to compromises, and that's just a sort of illustration of the one that we've taken here. But I think for our purposes, it's an absolutely valid example. So George has really talked a little bit about how we use it internally, and it's really powerful, and it really helps us to really inform our product development. And I think it's important to note that we have to do it at this scale, because it's not necessarily a linear scale from small to big, right? So we have to take these large data sets that are replicating the real world, because doing something on the small data sets or smaller data sets doesn't necessarily translate in a linear manner to what you might see at these larger scales. So let's just refocus a little bit and think about the wide range of mobility data use cases that are out there in the real world and in the sort of external examples. And I'm just going to focus on 3 here today. There are obviously a huge suite of use cases, many of which are in mobility and telematics and insurance and kind of very traditional mobility, but many of which are also in much wider sectors. And mobility data has lots of cross applicability. But just to focus on 3 that we've really teased out here, because they're really important in Singapore particularly, are to think about how this data set and how this data can inform things like Singapore's plans for the future in developing its transport network. So on the bottom left here, you can see Singapore aims to make all journey times, this is a government target, in the city and in the nation, less than 45 minutes by 2040. So to go from any point in the city to any other point in the city is going to take, hopefully, less than 45 minutes. So understanding origins and destinations of their existing journeys is really important for them to be able to identify hotspots and potential trouble spots in time and space that they can quickly and effectively help to redesign the network. And so having granular data, which doesn't just tell you the origin and the destination, but tells you how they move between the two, is really important for being able to understand and build that model out and understand the impacts of changes. The next one is pay as you drive. Now, as George said earlier, ERP in Singapore stands for electronic road pricing, right? So at the moment, they have these arbitrarily placed fixed gantries, which enable them to do kind of congestion charging based on where those gantries are on the road and how many people and how many cars travel below them. By moving to the satellite system, they'll have a load more data, but that will enable them to effectively give everyone an individualized driving pay-as-you-drive score price based on exactly how much mileage they use within the city-state. So this is a really, really great use case where they're moving to a much more dynamic digital system. They'll be able to sort of really be much more equitable in the way that they price people based on the actual miles that they use and the actual places that they visit during the day, rather than just the kind of fixed gantries that they happen to pass through. This is really exciting, and being able to test the kind of responsiveness and the ability to pull out that data using our platform and using the synthetic is a really great start point for them to understand how this system could be built and will be built on their satellite data when it goes live. And the third one I'm just going to focus on here is obviously Singapore as a nation has a duty of kind of care to its citizens, and they're always really interested and really looking at the ways that they can improve the quality of life and the safety of their citizens. And so, you know, with a platform like this, one of the benefits of this is that we have the raw data available, and it's not aggregated and it's not summarized, it's available in its raw form, which means that it's really powerful for looking at both the micro events, individual vehicles, and the collective events, the overall traffic patterns around the city. So for instance, in the case of an accident occurring in the city, we can really quickly zoom into the specific vehicles that were involved in that accident, understand the driver behaviors that perhaps led to that incident occurring. We can do that by zooming in from that classic needle in a haystack problem, finding those vehicles and really identifying and understanding their behavior. But we can also look at it collectively. What was the impact of an incident like that on the overall traffic in the surrounding area? Did it cause an average speed reduction as everyone had to slow down to avoid the incident? And how quickly were people diverted and around the area of affected area as the network responded to the incident? And this is really important to inform how Singapore adjusts its network and how it builds a more robust network in terms of transport that's safer but still remains just as efficient or becomes even more efficient over time. So that ability to sort of zoom really quickly between those two scales of data is really important for being able to do these kinds of analysis and build these use cases. And that's why having these large scale data sets that are really granular and being able to access them in their raw form is really important. So you don't lose any of that richness of the data. So that's 3 use cases from Singapore. Obviously, I've said that there are 100 more use cases that you can think of in mobility. And of course, if you marry these data sets with other data sets, there are even more types of analysis that can be performed. So if you've liked what you've seen today, there we go. You can actually explore it yourself in one of our tools, GeoSpock DB Discovery, which is effectively our sandbox trial environment. And what we have in that environment is the synthetic that we've talked about today, so the really large connected vehicle synthetic data. But we've also put in a load of open and public sources of data cited in Singapore. So there's some taxi availability and congestion and traffic type data there. There's some environmental air quality and temperature type data. And there's also some demographics information as well, all packaged up in the Discovery platform. And we make that available. So we host that on our GeoSpock kind of AWS cloud, but we enable it to be accessed and queried by third parties through their AWS cloud and ultimately hooked up into your data science environments and your business intelligence tools. And what we use this for is to give people a chance to get a look feel of GeoSpock, see how we work and see kind of the types of queries that we are really well suited for and the kind of real world applications, but also to give you a chance to experiment with these large scale data sets and with fusing those with other types of data to build out kind of quasi realistic use cases and applications before then maybe testing them on real data. So if you're interested, you can sign up on the link there, or you can always just get in touch with me afterwards. I'll make my email address available to everyone here. It's fully supported. It comes with all the kind of integrations and how-to guides to get everyone up and running. So it's a really great resource if you want to play around and you want to explore this kind of data more. And with that, I would like to thank everyone for listening and thank George, obviously, for his contribution, his presentation, really interesting. And we'll close there and open up for any questions that there may be on the floor. So thank you very much.
Thank you. Yeah.
So I'm just going to come out of present mode for a second.
Okay, let's see what questions are coming in. So how are bugs manifested in the benchmark? So this is an interesting one because it can happen in various ways. There are obvious ones that happen, such as when we try and run a query, it may just throw an error. So it may just completely not work. This could be because of the query itself, or it could be because of machine configurations. But sometimes there are ones that are actually harder to find. So for example, when we do testing, we also do testing of different scales. So when we look at different time scales, and if we say, for example, CPU usage, it doesn't correlate quite as we expect it to, we can feed these results back to engineering, and then we can say, here's kind of what's happening. Can you investigate that? And then usually they can find a quick fix to these sort of things. So actually, yeah, there are different ways that they can happen. And actually benchmarking really does help find these solutions. Good question.
Perhaps I'll take a question now, which is on how we would, or whether we can replicate the data in other places. And I think, the short answer is yes, we can obviously replicate that. And I think we've done it in Hong Kong as well. So another similar sort of large-sized Asian city. I think, as George maybe has had a bit more color in, the process effectively would remain the same, but the input variables, obviously the seed trips, the sort of the source of those origins and of where those trips are going is the kind of key data that perhaps it would be change. It would be the variable that we would need to change for doing a different location. If that's correct, George.
Yeah, so as long there's two factors that really account here. So as long as we have the seed trips so that we get some realistic data, and also that our routing engine has the ability to create some routes between said areas, then yeah, this could be transferred to any city and create some quasi-realistic data to any sort of scenario that's required, really. How long did it take to create the data set? So actually this was kind of done in two main parts, really. So the first part is actually to do with the routing engine itself, trying to configure that and make sure that works properly, because sometimes in testing and debugging, it wasn't taking quite the sort of routes you can imagine a normal person would take. So you need to make sure it takes sort of optimal routes as unless you're trying to do a scenic drive, as a normal person really would. And then also there's the second part of making sure that when we run our code and we create the code for the synthetic generation, we want to make sure that we don't overload the machines, because in the initial stages of it, we got to the point where we were in each machine has a certain amount of memory, and we were kind of reaching that memory point, and then they wouldn't be able to send any instructions because they were so full. So we had to make some workarounds to kind of say, right, how do we get it so that we can efficiently create data and make sure it's doing everything it needs to do at the same time. So overall, it took, I would say, a few months.
I just had another question on what, can you just reiterate around the main compromises, if you like, or the lack of maybe congestion in the data set, and how the balance was sort of, why you chose the balance that you did in when you built the synthetic?
So that's an interesting one, because there are companies out there, and there's academic papers as well, that are trying to emulate real world congestion. And then when it comes to, there's very technical solutions to this. When it comes to that, it requires a major amount of resources. So for example, you may have a data set that's only 4 gigabytes in size, but to create realistic predictions of where they're going and where the congestion is going to be, that could take, on a data set as small as 4 gigabytes, it could take up to, say, 5 or 6 hours. So as you can imagine, you scale that up to 100 terabytes. If you try and do something for that, it's not going to be feasible, really. It would take way too long to get anything that's usable out there. So what we did was we created a data set where the trends are going to be what you're going to see roughly in the real world, but not exactly. And the reason being, we want to make sure that although the answers aren't going to be exactly what you want, when you run through a database, GeoSpock DB, it gets the exact sort of process that would actually happen in the real world with real data. So we collect and we scour the data set exactly how you'd expect, really.
So from the database perspective, it's a kind of realistic data set, but from perhaps the from the querying and the mechanics of the querying, they are accurate as they would be in the real world.
Yeah, precisely. Yeah.
Okay. We've also had a question about a little bit more information on the benchmarking that was shown at the beginning. So the benchmarking was performed by last year by a sort of an independent telco company based in Japan, major telco, Japanese telco. And the obviously GeoSpock DB was one of the results shown. The other result was one of the major, I think I can say one of the big three cloud providers analytics databases, right? And the results of that obviously showed that we were significantly faster and cheaper, but also gave the telco enough confidence that they've actually subsequently become an investor in GeoSpock. So they were pretty positive results, and they're pretty convinced by those results. If there are any more specific questions on that, we do have a white paper on our kind of performance benchmarking, which I'm happy to share afterwards. Great. All right. I think we've pretty much covered all the questions that have been coming in. So I thank you again to everyone who's been listening online. And thanks again to George for presenting and answering most of the questions there as well. And with that, I think we can wrap up now. So thanks everyone for coming, and have a good day. Thanks now.
Thank you very much.